Hello everyone. So in this particular video we are going to discuss all the previous year question of particular chapter properties of fluid in fluid mechanics for GATE civil engineering. So stay with me. We will be discussing all the questions in one go. Thank you. So let's start. So as we can see here, the very first question, which is group 1 contains the type of fluids while group 2 contains the shear stress, rate of shear stress relationship of different types of fluid as shown in the figure. So we have this diagram here where we can see the rate of shear stress. Rate of shear stress means we have du over dy and at the x-axis, and yield stress or shear stress we can say tau on the y-axis. So du over dy in the x-axis, tau on the y-axis. We have given certain groups, group 1 and group 2. We have names in group 1. The different types of curves are there and we have given the names: Newtonian fluid, pseudoplastic fluid, plastic fluid and dilatant fluid. So we have to match the type of curves with the names. So let's see what are the different types of fluid first, and then we can easily match here. This particular question came in GATE 2016 shift 2. So let's say see, we have specifically we have two different types of fluids. Like we have Newtonian fluid, we are having Newtonian fluid, and we are having another one is non-Newtonian fluid. Yes, so we know what Newtonian fluid and non-Newtonian fluid, how they are different, we'll see. So the Newtonian fluid, for this we must know that the fluids which obey the Newton's law of viscosity are known as Newtonian fluid. So what is Newton's law of viscosity? So that is given by a relationship. Tau is equal to mu du over d phi. That means shear stress is directly proportional to the velocity gradient. So what is velocity gradient? This particular du over dy. So it is directly proportional with the velocity gradient du over dy. Du over dy means change in velocity with the change in distance. So what is the effect on velocity when the distance is changing at different locations? What is the change in velocity? So for removing the proportionality sign, we are having a constant that we name it as dynamic viscosity. So here we have this particular Newtonian fluid with this relationship. Okay, now how the non-Newtonian fluids are different with Newtonian fluid? So I'll give you an equation that we already know that for them, for non-Newtonian fluid, we have the equation tau is equal to A du over dy to the power n plus b. So this is the equation where we know tau is the shear stress. Okay, d over dy we already know, velocity gradient. Now what is A, n and b? These are the three new. A is the your consistency index. So A is the consistency index and n is the flow behavior index, and the last thing B is the yield stress. So as you can see here, yield stress, right? This much they have shown as yield stress. So this yield stress is nothing but we denote it as B. So this is in equation of non-Newtonian fluid. Now these non-Newtonian fluid, in this also we know there is a concept of apparent viscosity. We should first understand that. According to that we can proceed further with this curve question, right? So this is dynamic viscosity. mu. Tau over du over dy, du over dy will give you mu. This is your real viscosity, right? Dynamic viscosity. So if we want to know what is apparent viscosity, that is given by d of tau with du over dy, mu star we can say. So that mu star is nothing but apparent viscosity. So this is your apparent viscosity. Now, in non-Newtonian fluids, we don't get real viscosity or else dynamic viscosity. We get apparent viscosities. So, this apparent viscosity we can say the value of mu star, right? Or mu apparent we can say. We will be getting this as nothing but if we compare it, right? So this mu star will be having a du over dy to the power n minus 1 into n. So this is the equation of apparent viscosity. So we have the equation that is apparent viscosity v star or v apparent, you can mu star or mu apparent, you can say anything. So that is nothing but d tau over d u over dy, right? So we have tau equation that is a du over dy to the power n plus b, right? So where du over dy will be there, that only will get the differentiation. So b will be 0 in this case because there is nothing called du over dy in this equation in the second term. So when we differentiate with respect to du over dy, so that is having power n, so n here, and we will get du over dy to the power n minus 1. This is nothing but the equation of your apparent viscosity, right? This is apparent viscosity. Now if I want to know the viscosity for Newtonian fluid, right? So for Newtonian fluid, we should remember that the value of A, please remember this, value of A should be 1, value of, please remember this, value of A should be mu, value of B should be equal to 0, and n should be equal to 1. So this is how we get Newtonian fluid equation. How? So if we put A is equal to mu, right? For apparent viscosity we put A is equal to mu, n is equal to 1, and du over dy, let's say du over dy to the power n minus 1, yani that means 1 minus 1, that becomes 0. So we get apparent viscosity is equal to your dynamic viscosity in case of Newtonian fluid. So this is the knowledge about Newtonian fluid. Let's go and see non-Newtonian fluid. So till now we have seen the difference between Newtonian fluid and non-Newtonian fluid. Now in non-Newtonian fluid also we are having different types. Newtonian fluid is done for us now. Non-Newtonian fluid we are having different types. One is time dependent and another one is time independent fluid, right? So first of all we will discuss time independent fluids. So time independent fluids are of two types. Time independent fluids are of two types. So that we have, first is dilatant fluid. Another one is, just I am telling you the key points to remember for the exam. Dilatant fluids also known as shear thickening fluid. Shear thickening. Okay, why shear thickening fluids? Why? Because as long as, see, dilatant and pseudoplastic fluids are time independent, right? So I will write here time independent fluids. Okay, so if it is not time dependent, it depends on the velocity gradient. That means it depends on the du over dy. So with the change in du over dy, the viscosity changes in this type of time independent non-Newtonian fluids. So what happens? The apparent viscosity, when the apparent viscosity decreases, okay, when the apparent viscosity let's say first increases we will study, right? So when your apparent viscosity, that means mu star, the value of mu star increases when we are having d over dy increase, right? So with the velocity gradient increasing, we are increasing the, if the fluid's viscosity increases, that is dilatant fluid. So and when with d over dy increasing, if the fluid's apparent viscosity decreases, that is what? Pseudoplastic. So if the viscosity is decreasing, right, so what we'll call it as? We'll call it as shear thinning fluids, right? And when viscosity is increasing, it will be called as shear thickening fluids, right? And for example, with the amount of getting shear stress, right, so we'll get, for example, we'll be having a suspended starch solution. So if we are giving more velocity gradient, the starch will become thick after more viscosity gradient. And sand and sugar solution, right? So sand, sugar solution, everything is increasing, viscosity increasing with respect to the velocity gradient. So if we talk about pseudoplastic fluids, so pseudoplastic fluids we have also known as shear thinning. So with respect to the velocity gradient, increasing velocity gradient, the shear will be less and the viscosity will be decreased. That means for them, example, we have milk, right? We have gelatin, we have paint. So as long as we mix paint, it becomes thinner and thinner and thinner. So these are some examples for pseudoplastic fluids. Now this is about time independent fluid. And one more thing you must remember, that du over dy depends on du over dy, along with that it is having b equal to 0 in this condition. So for all the time independent fluids, we have one equation for them. We have tau is equal to mu what? For the time independent fluids, we have the equation as b is equal to 0, we are having a du over dy to the power n. And if n greater than 1, n greater than 1 means velocity gradient is increasing, right? You will be getting dilatant fluid, and when n is less than 1, we will be getting pseudoplastic. Now let's discuss the time dependent fluid and what are the types. So as we can say, here we can see the value of b is 0 and time independent. Let's relate it with our question. What I have told you, what is b? B is the yield stress, right? So when yield stress is 0, that means you can see here in this, if the yield stress is 0 here, right? So the value of yield stress 0 will be at this point. So all the fluids, see, first of all, yield stress is not at all in the Newtonian fluid, and shear stress is directly proportional. So in which case shear stress will be directly proportional? It will be here. This is your Newtonian fluid. And one more thing, when I was saying that shear stress, here also yield stress is 0. Yeah. So time independent fluid either will be 4 or 3. Okay. How we can see that? See, here n will be greater than 1 and n will be less than 1. Okay. When n greater than 1, it is dilatant. N greater than 2, it will be pseudoplastic. I remembered it like that in the alphabetic order A, B, C, D. Okay. D comes first. This is first. N comes after that. N. P comes after N. So it is pseudoplastic. So this is how I measured. Now, well, so till now what we have discussed, according to that, if there is shear stress, we are having the fluid that we call as time dependent, right? Time dependent. So if time dependent, that also um, see, for time dependent, we are having Bingham plastic, okay, that will be straight. It will take some initial yield stress, then only it will act as a plastic fluid, okay. So it will be Bingham plastic if that is straight after some shear stress. That means after some initial shear stress, the value of initial B, okay, that will be your time Bingham plastic. And thixotropic and rheopectic, two more types of fluids are there. Here we have only, see, plastic, dilatant, Newtonian. So according to the question, I am not going into the time dependent part, but you know that this is your Bingham plastic. There will be another curve like this, okay, that also initial curve will be n is greater than 1, this curve will be n is less than 1, and that also you can relate. What comes first? R, right? R is rheopectic, so R, and this is thixotropic, T upward. So like this I have remembered rheopectic and thixotropic. So this happens there. Curve 1 is ideal fluid. This is ideal fluid, and ideal fluid will be having no shear stress, only rate of shear strain, rate of shear, okay, and it will be ideal fluid with the curve 1. Now any curve, okay, after a particular yield stress is a plastic fluid, right? Even if it is a thixotropic, even if it is rheopectic, even if it is Bingham plastic, all three are all three come under plastic fluid category. So now if we match, the full answer, we are having Newtonian fluid as curve number 2, right? So it will be curve 2. Pseudoplastic is curve 4. Sorry. Plastic fluid is curve 5. Dilated fluid is curve 3. So we have P2, Q4, P2, Q4, R5 and S3. So we have the answer here 3. So this is the full explanation you can get here in the first question. All Newtonian, non-Newtonian knowledge you are having right now. Now you can put it in any question and do it. So now we will discuss the second question, that is dimensions of kinematic viscosity. So see, till now we have discussed the dynamic viscosity. Dynamic viscosity, you should remember the dimensions, right? So very important, dynamic viscosity is, here I have shown tau over du over dy, right? So if I say the dimensions, the dimension of shear stress is Newton per meter square, right? I'll write it something like this, Newton per meter square. What is velocity? Velocity is meter per second, right? And there is dy also, okay. So meter per second is velocity, and we are having another meter here, right, with for the distance, right? So meter cancels, second will go upward. We are getting the dynamic viscosity for unit, that is ns upon m square. Newton second per meter square is the equation of dynamic, is the unit of dynamic viscosity. See, there is one more term, kinematic viscosity, that we denote as nu, right? So the kinematic viscosity is nothing but mu upon density. Another term needed in fluid mechanics, they have divided dynamic viscosity with the density and they got kinematic viscosity. They have named it as kinematic viscosity. So if I put the dimensions of dynamic viscosity and density, so what will I get? We'll see. Newton second per meter square, and we have density. What is density? Mass upon volume. kg per meter cube, right? Meter square, meter cancel. So if we put Newton's value in kg, right, we can change it in some other thing. So that will be, what is Newton? Newton in terms of kg, kilogram meter per second square, right? So we'll put it here, kilogram meter per second square. We have already kg here and already second and meter here, right? Second cancel, meter will be meter square, kg to kg cancel. We are having meter square per second. So the units of dynamic viscosity is nothing but meter square per second. So let's see what we have. We have here and dimensions, right? So dimensions here, meter means L, okay, second means time. We have meter square, L square upon second means time. So we have answer C. So let's do third question. Cavitation is caused by. So the cavitation is caused by low pressure. Answer will be low pressure, but how, right? So you must remember, you should understand that there is something called vapor pressure of any fluid, right? So the vapor pressure is the pressure at which this is the minimum pressure, like after which the fluid will go and become vapor or vaporize, right? So this is the pressure at which fluid vaporizes. So if the pressure is less than vapor pressure for any liquid, see, this is the maximum pressure, okay? If the pressure is less than this pressure, all the particular fluid will definitely vaporize, right? So if the pressure is more than this vapor pressure, fluid will be in the state of liquid. Otherwise it will go and become vapor if the pressure is less than vapor pressure. So in this case, what is cavitation? Okay, so cavitation is in pipes. Sometimes, like if this is the pipe, right? Sometimes, see, wherever we go from a distance, like at a height, pressure becomes low. We know, right? We know that if we go at higher altitude, the pressure becomes low. So it works here also in case of pipes. And generally, at higher altitude, pressure becomes low. So when the pipe is in vertical direction, vertically it is at upward direction at some point, we see that the pressure of the fluid at this particular point sometimes can get less than the vapor pressure, okay? Pressure of your fluid can become less than the vapor pressure. So what happens now, if the pressure is less than vapor pressure, fluid will vaporize. So fluid vaporizes and becomes bubble here. Now this is the pipe, right? Fluid has to go and fluid has to come. So when this fluid comes down, if it is coming down, the pressure will increase, right? So when the pressure increases, the pressure comes on the bubbles, and the bubbles start busting. Okay, these are the bubbles that start busting. With bursting sound, this bursting sound we hear in the cavitation. This is known as cavitation, this whole phenomena. And due to this, there is rusting on the inner wall of the inner wall. Some bubble marks, inner wall will be damaged of the pipe. So this cavitation should not be happen in any pipe. So for that, we must ensure that the liquid pressure at any point must be greater than the vapor pressure. So why the cavitation happens? We can see the reason is low pressure. Low pressure. Okay. So we have done 3 questions. This particular question came in GATE 2000, and we'll see the previous other questions that came in older GATE exams. That is question number 4. With increase of temperature, viscosity of a fluid does not change, always increase, always decrease, increases if the fluid is a gas, and decreases if it is a liquid. So for this, we have to understand the effect of temperature on viscosity. So this particular question number 4, We already know the viscosity of liquids depends on the temperature. But how? See, we already know the viscosity works differently for liquids and works differently for gases. Okay, so here if we say viscosity of a fluid, particularly liquids, that depends of cohesion. Okay, so due to cohesion the viscosity is there in liquids. How? So when temperature increases, now I have to see the temperature effect on viscosity, right? So when the temperature increases, there is a increase in the molecular energy, right? When the molecules have more energy, they are free to oppose the intermolecular forces, right? So so because of that, the molecules oppose the intermolecular forces and run freely, and the viscosity becomes less with temperature increase in case of liquids. But when we talk about the viscosity in case of gases, so in gases you can see, we know that in gases the viscosity is mainly due to the molecular collision. The more collision, the more viscosity of the gas, right? So when we increase temperature, just think, when we increase temperature, molecules have more energy. Okay, they collide more and more, right? So the collision increases due to the temperature, and if the collision increases, the viscosity increases in terms of gases. So we know increases if the fluid is a gas and decreases if the fluid is a liquid. So with this we have done with question number 4 as well. Question number 5 is the unit of dynamic viscosity of a fluid. Just a few minutes ago we have seen the unit of dynamic viscosity, Newton second per meter square. So it should be here, Newton second per meter square. Answer B for 5. So the sixth question is, a fluid is one which can be defined as a substance that has same shear stress at all points, can deform indefinitely under the action of smallest shear force, has the small shear stress in all direction, is practically incompressible, right? So what should we do it for this? Same shear stress at all points doesn't work, right? Can deform indefinitely under the action of smallest shear force? Yes, it acts, but see, it can deform indefinitely, but there are some forces. See, for example, water. If we put water at some place, right, it's some slopey place, right? So it will go down, but at some place it will stop because there is friction, right? There is friction, there are surface tension, these kind of forces are there, but it can definitely, like, it can indefinitely deform under the small shear force. It is correct. Has this small shear stress in all direction? It doesn't seem good. Is practically incompressible. Fluids are compressible practically, but value is very low. So the answer according to me, it should be can deform indefinitely under the action of smallest force. So this is the question number 6. Now question number 7 is, if for a fluid in motion pressure at a point is same in all direction, then the fluid is, okay, pressure is same in all direction, then which type of fluid can be? Is it a real fluid? Is it a Newtonian fluid? Is it an ideal fluid or a non-Newtonian fluid? So this type of fluid is known as ideal fluid, because in any real fluid there cannot be pressure same in all directions, right? See, on the surface will be having different pressure. Okay, in case of ideal fluid there is no shear stress. Okay, so it can have same pressure in all direction, so it is ideal fluid. Now it is question number 8, that is, shear stress develops on a fluid element if the fluid is at rest, if the container is subjected to a uniform linear acceleration. Okay, there are two more options that I have missed somehow. C is if the fluid is inviscid, and D is uh, D is viscous and flow is non-uniform. Okay, it is viscous and non-uniform, right? So shear stress develops on a fluid element if the fluid is at rest, if the fluid container is subjected to uniform linear acceleration, if fluid is inviscid, or if the fluid is viscous and non-uniform flow is there, right? So see, they are talking about shear stress. We have equation of shear stress. We can write it here again. Tau is equal to mu du over dy, right? See, the if shear stress developed on a fluid, in which case, if there is a viscosity, that means it is viscous, and there is velocity gradient. And what is velocity gradient? Change in velocity with respect to space, and change in velocity with respect to space, change in flow parameters with respect to space is known as non-uniform flow. If there are changes, see, if there are no changes with respect to space in flow parameters, that means velocity, acceleration, pressure, right? So that will be uniform. If there is change in these particular parameters, it is known as, with respect to space, it is known as non-uniform. So it will be D definitely. Flow, for shear stress to be developed, there should be viscosity, there should be non-uniform flow. So question 8 is also done. Question 9, let's see. We have continuum approach in fluid mechanics is valid when the compressibility is very high, the viscosity is low. Third option is the mean free path of the molecule is much smaller compared to the characterized dimension. And D is M is greater than, much greater than 1, where M is Mach number. What is continuum approach? First of all, we should understand that. So continuum, we should understand that it is a area that the scientist or the investigators assumed that can be divided and divided and divided multiple times, in infinitely, we can say. So that makes it possible to investigate the movement of matter on the very smaller scale, right? So, and one factor that is very important in this, that is mass density, molecular density, you can say that, the density of molecules on the matter, right? So that is molecular density in the validation of continuum, and that molecular density is characterized by mean free path, characterized by mean free path. Mean free path, what is mean free path? It is the distance between two molecules, right? So if the collision happens, there will be more and more collision, lesser and lesser will be the distance between two particles. So you need to remember, right, continuum approach is directly linked with mean free path and directly linked with uh, molecular density. So here the mean free path of the molecules is much smaller compared to the characteristic dimension. So it is the correct answer. Why molecular path is very smaller? See, what happens here, it is already calculated that the statistic average distance of molecules travel between two successive collisions, if the mean free path is very small, okay, mean free path is very small as compared with the characteristic length, the flow domain, that is molecular density, is very high. Matlab, that means if the mean free path is very small, molecular density is very high. Smaller and smaller the path, the density will be more molecules will be there. See, before collision, if they are taking less distance for collision, more molecules are there. That means it can be treated as continuous medium, right? Continuum means less mean free path, more the continuous medium. So it is saying the mean free path of the molecule is much smaller compared to the characteristic dimension. So it works for the continuum approach if mean free path is much smaller. So this is the question 9. Now we are having question 10 that came in gate 1989. Surface tension is due to what? Surface tension is due to first cohesion and adhesion, cohesion only, adhesion only, none of the above. So surface tension is, we all know, is just because of cohesion only. So surface tension, what is this? This is a cohesive force which develops between two immiscible fluids, and uh, and that develops the tension on the surface. That's it. So here the chapter ends. All the previous year questions we have discussed for properties of fluid. We just have, okay, and we got all questions in 1 mark, so we need to remember that. I hope you guys enjoyed. I hope you have studied all the questions. You don't have to go back and study again. You just have to open this playlist, go through all the questions. I'll be uploading continuously now. Thank you.